Are you able to hear and see okay online? Great. Okay. You guys can see? Okay. So, any questions from last time? So far we have AC power, so understanding all the terminology for AC power and calculations for those terms. And then we move to a maximum power, which is when you need, oh, I don't have it on this one. Let me go back to 17. Okay, so being able to calculate average power, root mean square, complex power, and understanding that the complex power is that VRMS times the complex conjugate of IRMS. And our RMS value, remember, is the magnitude over the square root of 2 for a sinusoid, which is most of the forms that we're going to see. In rectangular form, you can find the real power and the reactive power. In polar form, you can find the apparent power and then the angle, which is associated with the power factor, PF. And PF value is the real portion in rectangular form of the power over the apparent magnitude. Okay. All right, maximum power transfer. So next Monday and Wednesday, you'll watch maximum power transfer problems. So make sure you understand how to do those. You're going to calculate the load. It will be impedance, and then you take the complex conjugate, which means you're taking the J and swapping it with a minus J. And then power maximum will be 1/8 of the magnitude of your Thevenin source. So if that's polar, you take the magnitude portion of it only and square it, and then you take the real part of the rectangular form of the load that you find, okay? All right, filters was understanding the terminology, active versus passive filter, identify the different low pass, high pass, band reject, and then being able to understand what a corner frequency is, and that omega is in radians per second units. And resonant frequency was for the band pass and the band reject. That's that middle frequency. And then bandwidth is the location of, for a low pass, it will be up to some corner frequency. That would be considered your bandwidth. For high pass, it's after your corner frequency would be considered your bandwidth.
Bandwidth is just whatever it's passing, right?
When it's passing it, correct. Yep. So whenever it's passing it, so for band pass, it's going to be between those two frequencies. And then for band reject, it will be before a frequency and after a frequency. And those would be considered. So bandwidth is usually like a definitive number, so it's hard to say like band reject has a bandwidth and high pass has a bandwidth because it's more like anything above that. So
it's like a domain.
Yeah, so low pass is easy to say that bandwidth because it's a definitive number, and band pass is like, okay, I have that range, so it's a bandwidth. So usually I say it's operating range instead of bandwidth, just to make it a little bit more clear. But sometimes you need to find that bandwidth. In future classes, sometimes you need to find that bandwidth to be able to find that Q factor. So the Q factor was the other term you needed to understand. So for a high Q, it was where it's really narrow and really focuses in on a specific frequency, and a low Q gave you a wide range of frequencies. So for this one, the low Q is on the top where you can see like, yes, there's a wide range of frequencies it passes, but ideally you want it to like usually pass at one frequency. So you usually want a high Q. quality, quality factor. Yeah, so it does start for Q. Yep, quality factor is Q. Yep, so lots of terminology, but mostly for the filters, it's the concepts of it. So you're not going to really have to calculate, just identifying, so being able to make sure you are identifying those. All right. Okay. So let's start with this example. So in this example, you want to figure out what type of filter that this is. So in order to find out what type of filter, you're going to plot what is called the transfer function. So you need to find the transfer function. And a transfer function is a description. It's your mathematical description, I should say. Mathematical equation. V out in terms of V in. So you just need to find your V out equation in terms of V in. So I like to work with S, so I would translate these to be LS, 1 over CS, and then solving with that in mind. So go ahead and take a minute. Oops. LS. And solve this for VO. So you're going to leave V in as a variable in there and solve for V out. No, because this is an extraordinary node. So if you were to take the equivalent, I mean, you can take all of those in parallel, the 3 branches in parallel, as equivalent if you wanted to.
So I guess what I'm asking is, how are we supposed to find V in if?
So you're solving for V out, and you leave V in as a variable.
Negative. Or is it ground on the bottom?
I would put ground on the bottom.
Okay, never mind. That's all separate then.
Okay. So I'd put a ground on the bottom, because I like grounds on the bottom.
Put mine on the top.
You put yours on the top? Okay. You can, you just have to note that the polarity will be a negative. If you find V out with the ground on the top, you have to do a negative of it because of the way it's positive, positive and negative. Green.
Something so simple to make your equations so
Yeah. All right, so what will this equation look like to solve for V out?
So you're gonna be looking at V out over 30K plus V out over 40 nano S plus 10 nano S under 1. And then V out over 30K again. And then V out minus V in over 10K
Correct.
equals 0.
equals 0, yeah.
Correct. So there's your equation. So that everybody's on the same page with the equation. right, you guys get this?
I didn't do it on Wolfram.
Thereabouts? Okay. So once you get the V out equation in terms of V in, you just divide the V in over to the other side, so you have a quantity of V out over V in. This is called the transfer function. So this form here is what you plot, and if you wanted to just put it into MATLAB, this would be the syntax. So you define S as a transfer function variable. So you say S is equal to the TF, meaning transfer function variable S. And then H of 2 will be my equation. And so I put 1 over 10,000 K times the 1 over 2 times 30K plus 1 over 1,000 or 10,000 K.
The 30K and the 10K changed to 5 over 30K?
Yeah, it would be 5 over 30K would be fine. And then you can either write it as 1 over 40 nano S plus 1 over 10 nano S, or you can combine that to give you a common denominator for this term there. So this term as a common denominator would be 10 nano S over 40 nano S times 10 nano S plus 1. And so you end up with 40 nano times 10 nano S squared plus 1. So anyway, okay. Then you do Bode magnitude, Bode mag, H of 2, and then you can define the axis, or you can play around with the settings to be able to determine what they are on there. So the Bode diagram looks like this. For those that haven't seen a Bode plot yet, this is the magnitude on this x-axis, and then the frequency, again, is radians per second, so it's varying every single frequency and showing you what the magnitude would be for each frequency. This is called a log graph on this one, or log axis. So the x-axis is a log axis, so that's why you see that the lines are not evenly spaced. So these go by tens, so like 10 to the 4th, this would be 2 times 10 to the 4th, and then 3 times 10 to the 4th, 4 times 10 to the 4th, 5 times 10 to the 4th, 5th, 5, 6. Each of those lines, so it goes 2, 3, 4, 5, 6, 7, 8, 9 until you get to 10, and then it raises it by, 10 times 10 to the 4th is also 1 times 10 to the 5th. And so these are each called a decade, and decades go by tens. So 10 to the 4th, 10 to the 5th, 10 to the 6th, 10 to the 7th, 10 to the 8th, so on. So that's how you label the main axes on these graphs. So looking at this, what kind of a filter is this?
And reject.
There you go. So band reject.
Down.
Yep. And so would you say that this has a high Q or a low Q?
Low. Super low. Or small. Is it small? Or
It doesn't,
did small mean big?
I think
Q,
small
or-
means big, so it's really close
High
together, so I
Q.
think it has a high Q.
High Q
Q.
has a
Cause it's
pointy-
good quality,
Oh yeah, she did say that. She said high Q is this. Yeah,
cause it's better at doing its job.
I remember because it sounded funny. It sounded like high Q. High Q.
So this one's a little confusing
Is it weird cause it's upside down?
because
'Cause it's like-
it is upside down. It looks upside down. So you have to look at kind of what the main flat region magnitude would be. And then remember the corner frequencies are 3 dB, less than that. Remember you're looking at the averages or the RMS value. So whatever that value is, so if this is minus, making a guess, minus 10 dB, Your corner frequency is actually going to be -3 less than that. So it would be around here, you know, and kind of around here. So this would actually be your whole region.
So that's a low Q.
So this would be a low Q.
Got it.
And then these two values would be kind of your corner frequencies on there.
Why do you go 3 below? What's the corner?
So 3 dB is equivalent to 1 over the square root of 2.
Okay.
So you take whatever that magnitude and you could convert it back to volts per volt and then multiply it by over the square root of 2. So remember that the amplitude over square root of 2 was what we found for the sinusoids, for the RMS value.
Okay.
So 1 over the square root of 2 is 3 dB, so you just take 3 dB less. Yep, so this would be minus 13 dB. So the minus 3 dB is equal to 1 over the square root of 2.
Could you
Volts
back
per
up to your
volt.
H2 equation again? What do you do? So you're plotting the H2 in
Uh-huh.
there.
So that is this equation just from here. From here, I just
So we like solved
took those
for-
out. So I just left it without doing all the algebra. I just left it without the algebra portion of it and put it in that to plot it. But if I wanted to get a better, you know, so this is a little bit more reduced, but you would still want to get the factor of like taking out that S. So if I was to translate this back into the time domain, I need to, you know, reorganize it and do the mathematical
Okay.
manipulation of it.
And in the Bodhi plot, you can just use S.
Yep. So in the Bodhi plot, you can just say S is your transfer
Okay.
variable,
Okay.
and then it will plot this. So in this case, it actually is a low Q, and then omega naught would be approximately what?
What did you say?
What would be omega naught here?
5 times 10 to the 7.
Yep.
50 megahertz. Or 50.
Think, I guess. Wait, what?
Well, it's 5 times 10 to the 7. So it's 50 times 10 to the 6.
What's
You
wrong?
can also do Bodhi plots.
And it,
Just learned that right now. You can just do Bodhi plots on Wolfram. You don't need to put in MATLAB.
oh, really?
Yeah.
Oh, I'll let you do them in Wolfram.
You just type in Bodhi plot transfer function and then search that, and then it pulls up a transfer function lock, and then you can just plug in your function to that, and it'll graph it for you.
Okay.
Yeah,
So on that,
use
can you click like where that omega naught is? And does it tell you the value? Because on MATLAB, it will tell you the actual location value. Like if you click on that point, it will say its frequency equals. Okay, so in MATLAB, you can click on that 13, like you can hover over it until you get down to minus 13 dB, and then you can see the frequency there. So that would be where you could determine where your corner frequencies were, which is a nice feature of MATLAB, but you do have to know the specific syntax of it to be able to plot those. Okay, questions about this?
That wasn't too bad. Well,
Okay.
what question did we answer?
So this was just to find what filter this was.
Okay, that's it.
And
We
then-
found out it was a band reject.
And then what value of omega naught, which was that 5 times 10 to the
Which is
7th?
the distance between,
No, it's just that one location that looks like the center frequency portion.
oh, okay.
So right there at that point, so this point here,
That's W.
naught,
Naught.
W naught. And then this would be WC1 and this would be WC2. But they're hard to kind of see there.
Okay.
So I'm not going to put values in there, but just identifying where they were. And then was the Q high or low? Those were the questions that were asked here. All right. 18. Okay, so now we're going to move to Fourier's. So here's our circuit. On this one, we want to find IC of t for the different inputs. So the first input is 10u of t. So solving this using Fourier instead of Laplace, we're going to look at the Fourier transforms instead. So,
Can you go back for a second? Just like copy down that.
sorry, I'll give you guys a minute to draw it.
Is that nanofarads?
Millifarads. So 0.25 millifarads. So what will be your equation to solve for IC of t here, or IC of s, I should say?
So when we did like Laplace transforms, we did transform with time-dependent components. Do we have to do that with Fourier as well?
Yep, so with Fourier, you just don't have to worry about the initial condition.
Oh, we don't need to worry about the initial condition.
Correct.
So like it's just the
1 over
resistive part, or like 1 over CS?
1 over ZS or LS.
Or, okay.
Yep, that's it.
Okay.
So that makes it a little easier.
I started putting in the voltage source for this because now I need to do initial conditions.
Yeah, so don't have to do initial conditions, which makes it a little easier. I tend to like to leave VS until like right before I want to find the values. So if I was to write the equation here for solving for IC, what would I do? Or what?
VC first.
Okay.
VC best at least.
So you called this VC?
Yeah.
Okay. So what was your equation?
The input my equation would be VC is going to be VC divided by, or 0.25 ms. No, not divided by VC times 0.25 ms plus VC over 4k plus VC minus VS over 2k.
Sorry. Okay, so VC times 0.5,
0.25
0.25 ms, and then you said VC
over 4k,
over 4K.
and then plus VC minus VS over 2k
Correct. And?
equals 0.
Thank you. Yep. Okay, so there's your equation. And then this is to solve VC. So how would we get IC from this?
VC
VC over.
the capacitive resistive
So
value.
the first equation is going to be our IC, whatever that ends up being.
Okay. Right. Okay, so kind of multiplying these out. So you can solve for VC. So VC, combining all of your getting a common denominator, ends up giving you CVC. Okay, over.
And in this case, our VS is gonna be our V in, right? Or is that not?
Yeah. Yeah, this would be your VN.
So do we need to put VC over VS, or is that only for when we're finding the other thing?
So if you were to do this in Laplace,
Or
you
just
would do
wait,
10 over S.
We already know what VS is, so we can just plug that into the equation.
Well, you need to change this to either Fourier or Laplace, whichever one you're gonna use.
Well, I mean, like after we found the equation for VC, we don't need to plot it on the Bode.
No.
because- Yeah, I was just
Yeah.
getting confused about the steps there. And I realized like, wait a second, we're just finding IC.
Yeah, so this is just to solve it using the Fourier. Okay, so IC here is then 2 times VS wait a minute, times 0.25 milli S. So it's VC times that, and then
Oh,
3 plus S. So the 4K times 0.25 milli ends up being 1. So this ends up 5 times 10 to the minus 4. Times VS times S, all over 3 plus S.
where did you get the times 0.25 and S in top?
Yeah, where did the 2 come from at the top?
I know that one, four divided by two is two, so it's 4K and then 2K, so it's replaced with two.
We're doing IC.
Oh, okay, that
IC
makes sense.
equals,
But then how did it get on top?
VC times, okay, I got it.
It's 4K
Yeah.
and 2K.
So common denominator of 4K
Mhm.
from this side.
Oh,
Make a common denominator of 4K.
so VC is gonna be equal to VS divided by 2K times 0.25 MS plus 3 over 4K, right?
I don't know if I heard you right.
So you have
So
VC
4K is your common denominator here.
Yeah.
So you have 4K times 4K here.
Oh, I didn't do that, that's why.
And then this will be times 2,
Yeah, I have
2K.
that, but.
No.
just 2.
Okay.
And
Oh,
s-
oh, you get it all in the common denominator before you transfer the VS up to the other side, okay.
Yeah.
That makes more sense
We're
then.
good.
Okay, you see it now? Okay. So from here,
Now we just convert the VS into the estimate, right?
so we have to use, for Fourier, we're going to use S is equal to J omega. So your IC now becomes IC of J omega. And VS, when you change it over, becomes these delta functions.
Oh, that's my least favorite Greek word.
Yeah.
Just lowercase, the uppercase is fine.
So your VS becomes,
I thought it was always something like
Becomes
this.
10 pi times omega, or delta omega plus 1. Or is it plus 10?
10 over 10
So you
J.
multiply everything, both sides by 10?
Mm-hmm.
Oh, yeah, that makes.
Yeah. So remember, when you do it in the time domain, it just translates over to the Fourier domain.
So,
That's it.
but it would be 10 and then put that whole thing in parentheses, right? And that's where you get both the 10s from?
Yeah,
Okay.
I just wanted to double check. It's an omega inside the parentheses.
that is omega,
Okay.
yes.
Wait.
It does kind of look like a 10 inside of
I was like, wait, how did that get in
Is that a
That-
better omega?
That is a great omega.
Okay, I'll be more careful with that. Okay, so now we just plug this in for the rest of the equation. So 5 times 10 to the minus 4 times j omega. And I'm going to leave Vs on the outside of it. And then 3 plus S, or j omega, sorry. 3 plus j omega. And now you can multiply it by the 10 delta So you're going to want to watch next week also the Dirac delta function properties. So go and watch those videos. They're on the lectures. And the nice thing is that these actually end up giving you that this portion of it goes to 0. So when you translate it back to IC of t, you only have to be concerned with, that portion of it. So go through the derivation that I do to show that that goes to 0. And then looking at this, we have the j omegas will cancel. So we have 5 times 10 to the minus 4th times 10.
So wouldn't it just be 5 times 10 to the negative 3?
Yeah, you can do negative 3. And then you're really just going to be translating the 3 plus j omega, which is going to be the e to the minus at of u of t. So moving that back, this ends up just being 5 times 10 to the minus 3, e to the minus 3t u of t. And that's your answer.
How do we handle the j omega? Oh, those ones cancel out? Okay.
Yep, the j omega is canceled out. So I just did those cancellations. And then this already is in the form that you can match to the table, so you can just do e to the minus 3t. Where'd I lose you?
Writing some stuff down, and then we had an answer.
Okay, so the 10 pi
Yeah.
delta function, when you take the inverse, that actually goes to 0. The integral of it goes to 0.
Okay.
So that's what you're going to watch in the derivation that I do on the videos. So that portion goes to 0, so you're just left with the 10 over j omega.
Okay.
When you multiply that, the j omegas cancel. And then remember the constants on the top just come out, so that's 5 times 10 to the minus 3. And so you're just left with the 3 plus j omega in the bottom.
Okay, and then that.
And then you use the transform for that.
Oh. Easy peasy.
And that's it. So that's where that came from.
Okay.
All right.
Very good.
Okay, we have a visitor. Oh. So if you guys want, we have a very small class today. They all came on Wednesday.
Okay.
What are you talking about? Everybody's here.
Got the whole game.
We could come back on Wednesday next week or some other time if you wanted
It would
to.
have to be next Friday. with
Yeah,
the
Friday.
class.
Yeah.
The Friday before Easter weekend, so.
Yeah. So if you guys want to be, so we have some people online.
Okay, cool. But Tiff, did you have a USB?
Oh, I do
Slide.
not.
Okay,
I have an adapter.
Do you have an adapter? Awesome. Thank you.
that'd be awesome.
I think yeah, I
Thank you.
Yeah, usually faculty and students all carry various adapters at any
Yeah.
given time for this kind of stuff.
do. The MacBook, I have to have that thing nowadays.
Yeah, you do?
Can't do
That's a slick adapter too, by the way. Look at that, that is cool with the HDMI
Put a
and
lot,
three.
yeah.
Yeah.
Yeah, USBs.
Not now. Okay.
So while Angela's pulling that up, I can introduce myself a little bit. For those of you guys who don't know me, I'm John Polke. I manage the advising department. I have been the graduate coordinator, the PhD and master's students for the last several years. And now I've kind of worked into a more administrative role, supporting undergraduate advising.